Hello folks, so I was watching the previous video that I had made on bond model, and any of you who has recorded your own videos, sometimes it's not the best or the most pleasant experience watching your own videos. And what I realized was that I had made a mistake in the previous video of bond model, and I had made a huge mistake. So I want to fix that in this video, and also want to take this opportunity to explain this bond model a little more, because this is a very useful model. It helps us to develop an intuitive feeling of how band structure comes from and how dopants works and so on. So in the previous video, when I was explaining this video, I had mentioned that you get 4 n states, or you get 4 states from each of the atoms in silicon. And this was a mistake that I made. In fact, you don't get 4 states. You actually get 8 states from each of the atom. So we, in the case of silicon, you have your outermost shells are 3s2 and 3p2. So our 3s shell, it has 2 states, and our 3p shell, it has 6 states. So in all, we have 8 states contributing from each atom, out of which 4 are occupied. So I had misstated that actually there are 4 states. There are in fact 8 states coming from each atom, out of which 4 are occupied. So if I have n number of atoms, the total number of states that I would have is 8n, and these will split up into these 4n states which are in the conduction band, and 4n states in the valence band. And the 4n electrons are distributed between these 4n conduction states and these 4n valence states. In fact, when our temperature is 0, all these electrons are occupied in these 4n valence states. So let me give you a little more color on how do these different shells contribute to the band structure in the case of silicon. So what I have over here is I have the silicon orbitals. So I have 14 electrons in my silicon, and 2 of them are in the 1s shell, and then the remaining 8 are in the second shell, and the remaining 4 are located in this outermost shell, that is our third shell. And out of these 4, 2 of them are located in the 3s orbital, and the remaining 2 are located in the 3p orbital. And if you look at the total number of states which are available, so this 3s orbital has 2 states available, and this 3p orbital has 6 states available. So in all, there are 8 states which are contributing to this outermost shell in this in the case of silicon. So now what happens as you try to decrease these interatomic spacing? So if you have these atoms which are far apart, these individual the electrons in these individual orbitals are not interacting with each other. But now when you tend to bring them closer, these electrons starts to interact, and what we see is that most of this action is located in our electrons in the outermost shell. So if we look at the case of electrons which are located in shell number 1 or shell number 2, and if you look at how these are behaving, so there's not much change when you bring them closer, or you even bring them closer to the distance of your lattice. And this is because these electrons which are in our innermost shell, these are bound very close to the nucleus, and even when you bring these atoms close to each other, they still remain very closely bound to the electrons, and these shells still remain very closely bound to the individual atoms. And so most of our action is happening in this outermost shell, or in this third shell. And what we see over here is that when you start to bring them closer, these atoms close to each other, these individual orbitals, the states in these individual orbitals, they start to split up and form these continuous bands. So if you look at the states in the 3s orbital, they split up and they form these two continuous bands, and then these states in the 3p orbital, they also split up and form these two continuous bands, and you see one of them rising in energy and the other one falling in energy as you bring the atom close to each other, as you decrease the interatomic spacing. And so what we see is that some of these bands are rising up in energy and some of them are falling in energy. And what you'd expect over here is that you would expect that these states from 3p, which are decreasing in energy as you decrease the distance, and then these states from 3s, which are increasing in energy as you decrease the distance, they should overlap with each other. So what you would expect is that these states which are coming on from 3p, and then these states which are increasing in energy and coming from the 3s orbital, they should overlap. But this doesn't happen, as you can see in this picture over here. You suddenly move from this condition when they're approaching in energy to this condition where they're already separated. So instead of having this overlap, you get something like this, where suddenly these states come close to each other and then they separate out. So why is there no overlap between these two individual bands? And that is because we have to conserve, or we have to obey the Pauli's exclusion principle. So if this was a case where these two bands were overlapping, then for an electron which is located at this particular energy, it could be either in the 3s band or the band coming from 3p. And that is, as we discussed in the last video, we have to make sure that we are not violating the Pauli's exclusion principle. And that brings us to an important point, that these bands or these individual bands, they don't overlap, and we will dwell on this later as well. But these bands which are coming from different orbitals, they never overlap with each other. And what you see over here is, now when you're approaching your lattice spacing, these bands are well separated in the case of silicon, and d is the distance, which is equal to your distance when you have formed your silicon lattice. And you see that now you have this continuous states in the conduction band, and these continuous states from the valence band, all of which are coming from this third shell. And you have a separation between them, and that is what gives you the band gap.